based on the books, what we are going to learn today is the following. You will have an idea on the branches of hardware-based cybersecurity. We will also learn about what is IP core protection and hardware security as a whole for logic and encrypted circuits. I'll also try to give you some examples of what hardware accelerators look like, followed by the different types of state-of-the-art hardware security techniques for securing hardware accelerators, some academic and industrial tools for hardware security, followed by giving some basic fundamentals and advanced research knowledge on IP protection of DSP cores, especially considering the forensic detective control portion of that. The audience will also learn about hardware obfuscation, both structural and functional type. We will also see about hardware steganography, hardware watermarking, and digital signature for IP protection, followed by biometric fingerprinting for hardware IP protection, and also design of secure compression hardware, which is specifically related to image and video compression. We'll also see about logic encryption and why do we need to secure medical imaging systems in the current generation of IoT and CPS, cyber physical systems. We'd also see about secured image processing hardware, certain reverse engineering scenarios, and finally, we'll design a secured RTL processors of discrete cosine transform based processor for image processing. Next slide, please. So these are some of the recommended books that I'm going to use today. These 4 books are written by me. They are all on hardware-based cybersecurity, published from IIT in the past 3-4 years. So for interested readers, one can adopt these books for further knowledge. Next slide, please. Okay, so what is hardware security and IP protection? It's an area of research which is emerging for semiconductor community, especially related to integrated circuits that focus on protecting designs against standard threats such as reverse engineering, counterfeiting, forgery, malicious hardware modification, and few others. It can be classified into 2 categories. First is it could be an authentication based approach, and second is obfuscation based approach. The obfuscation based approaches can again be further subdivided into 2 categories. First is structural obfuscation, and second is functional obfuscation. In structural obfuscation, what we do is that we try to transform a design into a functionally equivalent structure such that it becomes difficult and uninterpretable to an attacker during the reverse engineering process. While in the second case, it's an active mode of protection and it locks the design to encryption or encrypted logic keys by the application of some secret information by the IC vendor. Next slide, please. Now let us have a look at the typical SoC life cycle. I'm sure many of you may have heard the word SoC. It's called system on chip. So any type of consumer electronic systems that we see around us, whether it's a smartphone, smartwatch, whether we are talking about wearable electronics, they all employ SoC at the heart of it. So in an SoC life cycle, we start typically with several third-party multi-vendor IP integration, followed by integration of that in the SoC design house by a trustworthy SoC design vendor. Then it is outsourced to a foundry, followed by deployment in the real time. The interesting thing to note here is that in each of these stages, there are several types of cybersecurity protocols and algorithms that could be deployed to handle cyber threats. For example, at the IP vendor stage, there is a possibility of inserted hardware Trojans through backdoor entry. So we need Trojan resistant designs to improve detectability and trust validation. Second is in the SoC design house, there is a possibility of IP piracy and cloning. In that case, the deployment of hardware obfuscation or PUF or low-cost authentication method could be useful. Again, at the foundry stage, it's possible that the foundry vendor is untrustworthy, and as a result of that, there could be a possibility of hidden covert implanted Trojan, which could also be used for overproduction and cloning purposes. Again, obfuscation can come to the rescue here. And finally, at the deployment stage, it is possible that it leaks certain secret information, reverse engineering and cloning, which can again be tackled using cybersecurity methods such as side channel attack resistant designs, as well as designs which will help you to prevent reverse engineering. Next slide, please. Okay, now since I'm going to talk mostly about hardware accelerators, and these are those type of hardware chips and hardware integrated circuits used in cybersecurity, which are mostly used for image and signal processing applications. So they have wide application in the field of image and video, as well as they have application in machine learning and AI. Specifically, if you're talking about applications where you want to use it in smart city and IoT based framework, these cores of machine learning, AI, and image processing play a vital role. So some examples could be, for popular DSP and image processing applications, one of them could be finite impulse response filter. So people a little bit from the electronics or signal processing background, or people who work in image processing may have heard about this term. It's a type of digital filter that is often deployed in performing convolution operations for images and videos. Second is JPEG compression and decompression. This is used widely in medical imaging systems as well as in digital camera. So we usually have a dedicated intellectual property core, which is known as codec in short, that is responsible for performing compression and decompression. The convolution filter is mostly used for performing convolution operation at the hardware level, and these convolution operations could be for image blurring purposes, for image sharpening, image embossment, and image edge detection filters. They all are part of convolution filters. The fourth is discrete Fourier transform. So they're also responsible for performing special, image conversion to frequency image, or frequency spatial domain to frequency domain conversion of images and videos. So they also are important hardware accelerators used in many digital cameras and portable devices. And we also have something called DCD, which is a very important ingredient for lossy-based image compressions. So these are some of the very, very vital and crucial hardware accelerators, which are used in several consumer application, medical application, military application, and so on. And all these hardwares need to be secured against cyber threats. Okay, so we will learn about several different algorithms today, how those are actually being used to protect these hardware in the domain of cybersecurity. Next slide, please. Okay, so let me talk a little bit about the 5 most popular state-of-the-art approaches that have been published in several major IEEE transactions in the last 5 years. The first is known as crypto-steganography, and they are also included in my book, so interested readers can have a look at it as well. So crypto-steganography is the first one. Second is we have integrated watermarking and key-based structural obfuscation. Third is biometric fingerprint-based IP core protection, where you actually used a fingerprint biometric and embedded in a integrated circuit. Third is called integrated crypto-steganography and structural obfuscation. Here we exploit the advantages of crypto-steganography algorithm and structural obfuscation method, where we try to have double line of defense against counterfeited or cloned intellectual property cores, as well as against reverse engineering attacks. And finally, we have key-based hash chaining method. And this type of method is also used as a steganography algorithm for implanting digital evidence into the design. Next slide, please. So these are some of the in-house tools that have been developed in my lab at IIT Indore, which are going to be released academically and for commercial reasons in by the end of this month. So these 4 tools are serving several purposes, starting from handling fraudulent claim of IP ownership. Secondly, for handling detection of counterfeited designs. Third is detection of clone designs. And fourth is how we can thwart or hinder or impede reverse engineering process. So these 4 tools in totality handle almost all the attacks in a spectrum from one end to the other in case of hardware-based cybersecurity. Next slide, please. Now, let me talk a little bit about the forensic detective control method. So what type of forensic engineering methods that are used for securing hardwares, okay, in the context of cybersecurity. The first is known as single-phase hardware watermarking. The second is known as multi-phase hardware watermarking. Third is multi-level hardware watermarking. Fourth is hardware steganography. And the last one is digital signature-based watermarking. In the difference between multi-phase and multi-level watermarking is that in multi-phase watermarking, what we are trying to do is that we are trying to embed the watermarking constraints in different phases, okay, in different phases of electronic system level synthesis of an IC design. While in case of multi-level watermarking, what we are trying to do is that we will try to embed the constraints at different levels of abstraction, okay, of a hardware design. So some could be at the logic level, some could be at the RTA level, and some could be at the electronic or high level synthesis level. So we have divided the constraints into different levels and we keep on embedding it at the different abstractions. In digital signature based watermarking, what we have is basically we try to exploit the combination of crypto blocks as well as hashing blocks that can actually play a role in deriving the secret constraints that get embedded into the design as a digital evidence. And these digital evidence, in fact, help you in resolving fraudulent claim of ownership as well as in detecting piracy. Next slide, please. Okay, now also important to know what are the different classifications of obfuscation. Now, before we get into obfuscation, let me tell you the basic difference between what is the role of obfuscation and what is the role of forensic detective control. We should keep in mind that obfuscation is a method to thwart or impede reverse engineering process, okay, in a typical hardware cybersecurity process. Now, when I'm trying to say that it tries to hinder or impede the reverse engineering process, it basically means that it gives an opportunity to the designer to make his system into such a form that becomes unidentifiable or uninterpretable by an attacker. Because in order to perform the reverse engineering process, the person has to have thorough knowledge on the functionality as well as have structural analysis at the precise level done. Only if he is able to do that, then only he can covertly insert malicious logic such as hardware trojans into places that become undetectable during functional simulation and later manufacturing and testing phase. On the other hand, forensic detective control handles a different threat model. Here, the threat model, what I'm trying to talk about is the threat model about how we can nullify a false claim of ownership, okay? Or how we can detect piracy, or how we can detect counterfeiting, cloning, so on. So these are the two different branches of hardware-based cybersecurity that we are talking about here. And as I said, obfuscation, since it is actually responsible for thwarting the reverse engineering process and thereby trying to prevent insertion of covert or hidden backdoor entry trojans, they can be done using one of these methods or a combination of these methods. The first is known as compiler transformation based structural obfuscation of DSP circuits. Here, the DSP circuits are those type of applications which are mostly data intensive and therefore are hardware accelerators in a sense. The second is high level transformation. So here we could use several high level transformations. For example, we can go for loop unrolling, we can go for redundant operation elimination, we can go for logic transformation, we can go for tree height transformation, and a combination of that we can use to deploy to perform obfuscation of DSP circuits. The third could be hologram based obfuscation of DSP circuits. Here the design is camouflaged in such a fashion so that the attacker is not able to identify whether the design is a specific application or a combination of multiple applications. And the particular circuit of that application can only be activated by the application of secret key, which is only known to the designer and not to the attacker. And finally, we have the functional obfuscation, which is a combination of encryption, such as using AES, and we can also use it in conjunction with several intellectual locking blocks that will help you to reconfigure the ILBs in such a way that it becomes identifiable to an attacker. Next slide, please. Okay, now let me also talk a little bit about what is hardware steganography. Okay, so this concept was introduced very recently in last 2 years in the scientific community. Here, what is possible is that it is also useful in performing detection of IC counterfeiting and detection of IC cloning, as well as nullifying false claim of ownership. So imagine you have a brand X of original IC, and if you can derive the secret mark from the brand X of an original IP, it is probably not a counterfeit. If the secret mark or authentic stego mark is not present there, then it is considered to be a counterfeited design. On the contrary, if you have the same secret mark in brand Y, then it is probably a copy or clone of the IP, original IP. And if it does not have, then it is probably not a copy of the original IP. Next slide, please. Okay, now let me talk a little bit about the hardware security algorithms that are integrated with the HLs and logic synthesis phase of cybersecurity framework for hardwares. So the primary inputs could be module library, the DSP code, which is represented using data flow graph or C code, And we also have the real-time specification and the constraints of area, delay, power, energy, so on. And within the HLS framework, we can perform the DSE, followed by scheduling, hardware allocation, and binding, and finally generating the data path and controller of the processor. And during this process, within each of these phases, we can actually incorporate the security algorithm into the one of the subphases of HLS. Okay, now these security algorithms could be controlled by IP vendor secret information, such as the secret constraints, or they could also be the private key as we use in case of digital signature. And once these are embedded as part of the design during the in synthesis phase, we finally get RTL DSP circuit or an IC that contains the security information. Next slide, please. Okay, now let me talk a little bit about how to secure hardware accelerators using biometric fingerprint. This is also part of forensics, and it has been recently published in this year in IEEE Transactions on VLSI. So imagine you have IP vendor's fingerprint of the authentic IP vendor who wants to embed his information in the integrated circuit. So this IP vendor's fingerprint is captured using an optical scanner, and based on that, there is an algorithm that is employed to convert that fingerprint into its corresponding digital template. And once you have the digital template in place, then it can be used to embed in the hardware design. And that hardware will help you in detecting piracy as well as resolving false claim of ownership. Next slide, please. Okay, so this is the detailed process. So let me talk a little bit about it. Otherwise, it doesn't make sense for you to understand the algorithm. So imagine you have an input fingerprint of an IP vendor. The next step is to have a pre-processing block where you perform the FFT enhancement using masking. So FFT enhancement using masking is quite simple. You will have to find out the magnitude or the amplitude of the FFT. And finally, based on that, you can perform masking on that by multiplying it with a certain degree of power and then computing or multiplying it back with the FFT. And finally, you can perform an inverse FFT of that to get back to the spatial domain from the frequency domain. So once this FFT enhancement is done, then we can perform binarization. In binarization, what we do, we'll try to convert the entire image or the fingerprint image into a sequence of zeros and ones, basically, because we will try to compare it with a predefined threshold, and based on that, we will convert the entire image in the form of zeros and ones. Once you have the binarization done, then we will perform thinning. Thinning is done to reduce the thickness of the edge lines. So since in case of a fingerprint, we have mostly considered ridge ending and ridge bifurcation, hence we will try to reduce the thickness of the ridge line so that only we are concentrated on one particular pixel. Once this process of pre-processor is done, then we'll move to minutia extraction. In the minutia extraction, as I said, we are concentrating on two types of minutia points. First is ridge ending, second is ridge fork or ridge bifurcation. Of course, there are many others, but right now I'm just focusing on these two. Once you have the minutia extraction done, then we'll try to convert the minutia points into its corresponding digital template. And this digital template corresponding to the biometric fingerprint will be mapped onto the hardware security constraints based on encoding rules, okay? Secret encoding rules. Once these encoding rules are employed, we have now generated the corresponding secret constraints that will be implanted during register allocation phase of HLS design into the integrated circuit, okay? And that's how inside an IC, the actual biometric fingerprint of an authentic IP vendor gets embedded. Next slide, please. This is just a pictorial view of what I was talking about. If you have an input fingerprint image, you convert that to a binary image. From the binary image, you convert that to a thinned image. And once you have a thinned image, then you will have the last step, which is to convert that to a set of fingerprint with minutia points. Next slide, please. The secret biometric constraints for different fingerprint images are illustrated here. So you can see that the secret constraint that gets into the design of integrated circuit or hardware is mostly varying with respect to the different fingerprint images that we have captured. For example, the minutia points varies from 15 to 22 to 24, depending on what is the fingerprint image we are consuming. And depending on that, we'll again generate the number of zeros and ones that have a specific encoding meaning in the context of cybersecurity. Next slide, please. Similarly, for a same individual, the different fingers of an individual can also reflect different minutiae points, and these different minutiae points can again convert or get converted into different digital templates, which can again have different number of secret constraints of zeros and ones, which have a definitive encoded meaning. Next slide, please. Now, this is an application, a commercial application that we have designed in our lab at IIT Indore of JPEG compression hardware accelerator, which is responsible for performing compression of images. So when you capture a specific image in your camera, it by default gets always stored into .jpg format in the digital camera, folder. Okay. So in that, basically what I'm trying to say is this JPEG hardware that I'm talking about, JPEG compression hardware that I'm talking about, this hardware also needs to be secured with either biometric fingerprinting or needs to be secured with encryption, because this hardware is very much responsible for performing the encryption and compression of the pixel values. If the compression of the pixel values are incorrect, it could lead to a lot of problems when we want to view it in the context of medical images or in case of military applications. Next slide, please. So what is the way to detect biometric fingerprinting in a hardware accelerator? The very first step is to match the hardware security constraints, that is the number of zeros and ones of the digital template. Okay, so we have a digital template of the authentic or original signature from the owner, and then we also have a digital template of the fraud person who's trying to claim that ownership of the hardware. So the first step is to match the hardware security constraints in terms of number of zeros and ones in the digital template, in the bit stream. So in case they do not match, then of course we know that it's a counterfeited design, right? But if they do match, then the next step would be to match also the positions of zeros and ones. So here it is critical not only to match the number of zeros and ones, but to also match the positions of zeros and ones. If they both match, then we know that the correct owner is the person who will be awarded the IP ownership, and we can also prove who's the fraudulent claim of ownership here. Next slide, please. So in this graph, what we see is that, there is a variation in the minutiae points for different fingerprint images. This is obvious because not everybody will have the same number of minutiae points generated from the images of the fingerprint. So different fingerprints have the capability to generate different minutiae points. Next slide. And what I'm trying to reflect here in this graph is that based on the fingerprint images of a same person, okay, it is also possible to have the different fingers are generating different secret constraints, or for different fingerprint images, the secret constraints can vary from 350 to a very large value such as 540 and so on. So there's a huge variation in the number of secret constraints that get embedded. Next slide, please. Now, there's a new term called probability of coincidence. It's a mathematical metric through which we try to find out if by default a non-secure design has any information of the secret constraints by coincidence. So lower is the value of probability of coincidence, more secured or robust the design is considered to be. So as you could see that the probability of coincidence for different fingerprint images changes. Next slide. If you try to compare the design cost of JPEG compression hardware accelerator before and after fingerprint embedding, we'll see that mostly the cost does not change. So this is a very good sign because it actually reflects that the overhead of the algorithm is almost trivial or almost zero. Okay, so that's one of the plus points of using biometric fingerprinting approach for hardware security. Next slide, please. Okay, now how do we do the counterfeiting or cloning detection using proposed steganography? So this is pretty much what I've already spoken of previously, that you can use a stegomark to detect or classify whether it's a counterfeit or a clone by checking if in any other brand we have the original stegomark, then it will be classified as a clone, else it will be classified as a counterfeited design. Next slide, please. Now let me go through the basic steganography model. So when we talk of steganography, now steganography is also applied in images. Okay, many people who work in image processing, they are quite aware of this fact. Now steganography is also applied in hardware cybersecurity. In the context of hardware cybersecurity, steganography can be exploited in the following way. So suppose you have an embedded block. In the embedded block, you have a covered design data. So covered design data, in this case, the design could be any application that you want to convert into a respective hardware, whether that could be an image processing application, or video processing application, machine learning algorithm, whatever. Okay, so those can act as a covered design of the data. In the embedded data, we'll try to extract the secret constraints from the design itself. Okay, so we'll do an example so it'll be more clearer. Once these two are done, then we'll try to use a steganography secret key of the IC vendor to use only the constraints that the designer specifically intends to. And using these three information, we'll try to embed it and generate the stego data. The stego data, once it gets into an IP core, can again be extracted at the decoder stage using stego key. Next slide, please. So this is pretty much what I was already saying. So you have two phases. One is the encoder phase and second is the decoder phase. In the encoder phase, you will try to do the embedding of the steganography information, which is considered to be a digital information or digital evidence as per forensics. Once it gets into the design, then it is possible to retrieve for detection purpose at the decoder stage. Next slide, please. Okay, so this is another algorithm that has been recently proposed this year in our lab by my group. So this is known as key triggered hash chaining based steganography process for IP core protection. So it is a little complex, so I'll not go too deep into it, but I'll definitely try to make you understand in as simple way as I can. So let us start with the DFG representing the DSP application here. The DFG is nothing but the intermediate representation of the DSP application. So DFG is nothing but data flow graph, which is a graphical representation of the C code or the transfer function of the application that you have with you. Second is a module library, which is a library information through which you can actually evaluate the performance of your design. And third is a resource constraint. Resource constraint is also crucial because for any specific practical design, there is always a constraint on the power, performance, and area. So once using this information and the application we start, then we will apply a scheduling algorithm so that we can get a scheduled data flow graph. In the scheduled data flow graph, we can use that information based on certain encoding rules to convert that graph into an encoded bit stream. Now, since for an M operation, there is possibility that there are 2 to the power M number of combinations available. So that's why we have 2 to the power M number of encodings also possible. Okay. So once using these encodings, we have the value which is n bit, or we can call it m bit, whatever you want. Then we'll feed it into the pre-processing phase of the hash chaining block. In the pre-processing phase, we will try to generate the 1024 bits because a hash block that we have considered here is a hash 512 or SHA-512, which usually accepts 1024 bits streams. So this 1024 bit is generated and fed into the hash unit 1. Now that could be one of the ways to perform that could be if you have m bit information from the operations of the data flow graph representing the DSP, then you can append that with 1 followed by zeros to create 896 bits of the entire information, followed by adding 120 bit, which represents the length of the input bit stream. Okay, so that collectively gives you 896 plus 128 gives you 1024 bits for hash unit 1. Then you feed it into the hash block, which is having internal blocks such as round computation function blocks, where R, the number of rounds R is also designer specified. Once you do that, then you generate a 512 hash output. This 512 hash output is again fed into hash unit number 2, along with 380-bit information that comes from the second encoding in a padded fashion. Okay, so for example, the encoded information could be, for example, 15 bits. Then we pad it up to 380 bits. And again, the padding algorithm is known to the designer. It is not just a 0 padding or a 1 padding. And you extract a 380-bit information after the bit padding stage and augment it with 512-bit. Okay. Now, once you have that information, again, the 128-bit that you want can be from the length of the input bit stream followed by 1 and 000. So that gives you again 1024 bit for the input hash block. So this is something that we have a sequence of hash chaining blocks. The motivation was to do something a little bit similar to blockchaining technology here. Okay, you may have heard about this term blockchaining. And this hash chaining block basically has two different types of hashes. The first is the regular hashing, and second is the key driven hashing. Here the key driven hashing is nothing but the key that comes from the stego block. The steganography key is just one of the keys that the designer will apply in order to choose which encoding algorithm he intends to, because that encoding algorithm input is getting fed into the bit padding block. And finally, we pass it through n number of stages of hash chaining to finally produce output, which is 512 bit, okay, which is further subjected to bit stream truncation, because the designer should have the right and flexibility to choose the strength of the signature. So he will perform the necessary truncation and then conversion into respective stego constraints, and finally embedding it into a processor or any hardware or integrated circuit. Next slide, please. So this slide just tells you what are the different possibilities of the encoding. I've just given some examples of the 9 different possible encodings that you have. So just for example, if E1 is such that if you have an operation number and the corresponding control state both even, it'll be 0, else it could be 1. Other type of possible encoding could be if the operation number and the corresponding control step are of same parity, that is both are even, both are odd, then it is 0, else it is 1. So on, you could make 2 to the power of m number of encodings if there are m number of possible nodes or operations in a data flow graph. Next slide, please. Okay, so this is the detection process. The detection process is very similar to the detection process what I have already spoken of earlier. So nothing different than that. A slight only change is that here, since we want to detect the digital evidence in the design, in the hardware design, so we need to extract that information from the RTL circuit. So people who are unaware of what RTL is, it stands for register transfer level. So when we do a hardware security, what we're trying to do is we divide the hardware design into different levels of abstraction. Okay, the level of abstraction that I'm working here right now is the abstraction known as electronic system level or high level synthesis, in short, HLS. Okay, so the output of HLS is always an RTL design. RTL design means, for people who are unaware of hardware design, it is nothing but implementation of a hardware at the level of using VHDL or schematic capture. Okay, for people who use Altera Quartus or Xilinx tools in universities or in labs, then they should be aware of the fact that VHDL or Verilog and these languages are often used to design hardwares. So that is that RTL. So we inspect the RTL to extract that information. And then if that information matches with the digital evidence that you have implanted, then we know that it's an authentic digital evidence. If it doesn't match, then we know it's a counterfeit or a clone design. Next slide, please. Okay, so this is nothing but something called as a colored interval graph. So this just represents the interconnectivity information of different designs or DSP applications when you build a hardware using registers. Okay, so the reason why I put this information here is that this just reflects that the colors here are nothing but the different register numbers or different registers used in the design. And based on the information that you implant into the design, the register colors will keep changing. Okay, so register color keeps changing. So there cannot be, for example, if I have a constraint between two storage variables that gets assigned to the same registers, then that would mean that both those storage variables cannot be executed through the same register. So this is just an example of that. Next slide, please. So in this graph, what you see that there are some which are marked in blue connectivity and some which are marked in red connectivity. The blue connectivity are those connectivity which are there by default. So any design will have some default constraints, and the red ones are the constraints that have been implanted into the design due to the signature. Okay, as a result of encryption or as a result of watermarking or as a result of steganography, so on. Next slide, please. Next slide, please. Yeah. So this is one of the circuits of discrete cosine transformation that we have designed in our lab. Okay, and this piece of hardware block is used in image compression and video compression. Okay, specifically for lossy compression, when we are trying to compute DCT of an image, we'll try to go for 8x8 block of image pixels. So this circuit is responsible for computing that operation. So the point I'm trying to make here is that if you see the circuit, the red encircled pieces of the information are the ones where the secret steganography has been embedded. But just by optical inspection, it is absolutely impossible to comprehend where is the digital evidence which have been secretly implanted. It is only the designer, the actual owner of the IP, who knows that where is the secret digital information that has been implanted. So in case of fraudulent claim of ownership, the forensic analysis can easily reveal who is the actual owner. Next slide, please. Next slide, please. Right. Now, let me talk a little bit about digital signature. Okay. The motivation of digital signature comes from the fact that it is often used in digital certification processes. So people who work in networks, they may come across this term. But in the context of hardware cybersecurity, digital signature is slightly different. Okay. I'll try to go over the algorithm. Next slide, please. So IP core protection using digital signature. So the way is to use a crypto digital signature approach, which uses crypto hash function SHA-512 and crypto encryption function RSA, and then use it in conjunction with the encoding algorithm. So what are the generic steps? The generic steps of generating a digital signature is to first perform a bit stream representation of the DSP code. This DSP code is nothing but the application that you want to secure. Then we perform SHA-512 that consumes or takes input as 1024 bits and produces 512 bit based on RFC function. And then once it is done, then we perform post-processing followed by RSA encryption and then again post-processing. So these are the major steps. I'll give an example. Next slide, please. Okay, so imagine you have an IC/IP vendor watermark information that comes from the DSP code of the application or from any hardware information that you intend to build for any algorithm such as ML, AI, or image processing. And depending on that, then we will feed that information into the crypto hash function. And this crypto hash function produces a hash or digest of the information. Once that is there, then we will apply that to crypto encryption function based on the IC or IP vendor secret key, okay, which is usually the private key I'm talking about because it's an asymmetrical encryption, crypto algorithm. And once we feed it into the RSA block, which is the encryption function here, then we will finally get something which is known as digital signature of the IC and IP. Next slide, please. Okay, so now let me get into the algorithm of the approach that we have developed. So the major primary inputs are the DFG and the resource configuration. You construct a scheduling of that design followed by assigning of storage variables. Once that is over, then we will generate a bit stream. That bit stream can be used to calculate the digest of the bit stream. So this generation of the bit stream could be based on some encoding rule. And applying that will result into a bit stream which will be fed into the SHA-512 block that produces a digest of the bit stream. Once it is over, then we'll try to divide the bit stream digest into m blocks of size n bits, where each n bit block is further converted into its respective decimal value. Now that piece of block, which is marked in yellow, is the post-processing block 1. And once we have the respective decimal value, then we'll try to feed it into the RSA. Okay, so in this RSA, we will try to encrypt and finally produce, n number of encrypted values, which will be further concatenated together to produce a bit stream value after converting into a binary bit stream. Now, this binary bit stream of the encrypted concatenated output will have its own encoded meaning that will be converted into secret constraints to get into the design. Next slide, please. Yeah, so this is something which I've already spoken of, so I'm not going to get into this anymore. Next slide, please. Okay, in the RSA encryption, as you know, it's an asymmetric key encryption algorithm in which we have two distinct keys. So here we are actually using private key to sign off the information. Okay, so this is quite different than the encryption process where you actually use a public key and it gets decrypted using a private key. It is just the opposite. We will use a private key here, and that information is sufficient. So for example, if you have an RSA decimal input, which is 128 bits. Okay, so imagine the 512-bit output that you had that have been divided into 4 chunks of 128 bits. And this 128-bit information is a decimal RSA decimal input that has been fed, and the encrypted decimal output is shown in the next column. These will again be converted into encrypted binary equivalents, and that serves as the individual bit streams that needs to be concatenated to produce a final bit stream. And that becomes the final digital signature of the entire design of the vendor. Next slide, please. So once you have the digital signature, as I said, that depending on the choice of the designer, okay, who wants to secure the design, he can necessarily truncate the signature as per the strength of the information that he wants to embed. So therefore, this encrypted hashed bit stream is referred to as digital signature, which is further truncated based on the value. For example, if the vendor wants to select a value 15, so that becomes a digital signature of strength 15 bits, and the remaining will be truncated. Next slide, please. So on one of the important mapping rules could be to have bit 0 as follows, which is having it as converted into an additional or secret edge that could be added with prime node pairs of the colored interval graph. If you recall the colored interval graph, which I had shown in one of the previous slides, so this could be an additional edge between the node pairs which have prime numbers, and bit 1 could be an additional secret edge between node pairs which have even numbers in the CIG. Next slide, please. So for example, if you have an operation number and the control step, one of the encoding rules for converting a design into its respective bit stream before we start applying the hashing and encryption is that if the number of the operation and the control step both are having same parity, which is even, then it's given or assigned the encoded bit 0. If they have different parity, then it's given an encoded bit 1. Next slide, please. So this is one of the examples of how you can actually generate a bit stream of DCT core. DCT is discrete cosine transform. So this graph is nothing but the DCT function that you get, that you could develop and then convert that to a graphical form for an 8x8 pixel. So imagine the operation number and control number, since they both are odd, so we have a bit generated 0, and the operation number is even and the control step number is 1, so we have a 1. So similarly, you can keep on doing the remaining pairs of operation number and control step to generate the respective bit stream for every operation or node in the graph. Next slide, please. The experimental results that we had conducted, we found out that for any of these applications that we had tested, whether it's a bandpass filter, whether it's a lossy image compression using JPEG, whether it's a matrix multiplication, whether it's using autoregressive filter or inverse discrete cosine transformation, the design cost does not change too much, okay, after a certain signature size. So it becomes literally stagnant and saturated. Next slide, please. In this case, we try to evaluate the robustness of the approach using probability of coincidence metric, where the PC value, which is probability of coincidence, keeps on decreasing as we keep on increasing the size of the digital signature. And as I said, if you recall, the lower is the probability of coincidence, higher is the robustness and security of the design. Next approach, please. Next slide. Okay, now let me give you some idea about what is watermarking. So I'll start off by something known as triple phase watermarking, which has also been published 2 years back in IEEE Transactions on CAD by our group. So in this, the 7 variable vendor signature that you see here from gamma, alpha, beta, and all the variables of IIT and exclamation, they all could be embedded in different phases, in an assorted fashion in scheduling phase 1, in hardware allocation phase 2, and in hardware register allocation phase 3. And once these are embedded into the high-level synthesis framework, then we could generate the watermark for phase 1, watermark for phase 2, and watermark for phase 3. And integrated together, this becomes a triple phase watermark. So this is one of those multi-phase watermarking approach that I was talking at the beginning of my talk today, where you have a difference between multi-level and multi-phase watermarking. And once this triple phase watermarking is generated, then it could again be implanted into the RTL description of the hardware design. Next slide, please. So this slide shows the 2 designs that we have made in the lab. Okay, one is a watermarked finite impulse response filter versus a non-watermarked finite impulse response filter. Again, as I said, just by optical inspection of the two designs, it is literally impossible for any attacker to comprehend which design contains the digital evidence. Next slide, please. So this is one of the designs that we have made for an image filter that is used for 3x3 image convolution. And as I said in the beginning of my talk today, that image convolution is often used for performing image blurring, image sharpening, image embossment, and image edge detection. So these are all several functions that either work by cutting off high frequency or cutting off the low frequencies. And using this information, we can actually use this filter kernel coefficient to keep on convoluting with the image pixel values. And once it is done, then we can actually derive a hardware which can be obfuscated to secure against cybersecurity or cyber threats rather. Next slide, please. This is also an IP for several image processing applications that are often used in camera and smartwatch. We have all designed it in our lab here. So if you see, for example, these are the images on the left side, and based on pre-processing, if you feed the value of the matrix value of the image onto this structurally obfuscated blurred filter, useful for image blurring, it will produce the filter output that will again be subjected to post-processing. And you see the image on the right side is actually the blurred content of the image on the left. So this entire image on the right is generated by the hardware that you see inside the piece of box here. Similarly, for the next one, which is we have an input image, and you could see the image on the right is a sharpened image of the input image on the left. That is done using the sharpened filter that we have designed. Similarly, for vertical embossment, horizontal embossment, and lapless edge detection. Next slide, please. Okay, now let me speak a little bit about the role of compression in medical imaging systems. Before I move in, I just wanted to check how much time do I have? Hello, Amit, can you please tell me how much time do I have?
Hello. Sir, you can continue for more 20 minutes also, I think.
Yeah, you have the time, sir. You have the time.
Yes.
Okay, another 30 minutes I can do? Fine. Okay,
Yes,
thank
sir.
you.
Yes.
Okay, so now let me speak a little bit about the role of compression in medical imaging systems. Now, these medical imaging systems that I'm talking of is mostly CT scans and the ones used in MRIs. Now, the modern age healthcare systems heavily rely upon electronics and internet technology, as you know, to enable accurate and rapid diagnosis and advanced treatments, where electronics hardware are critical in the healthcare systems for processing of medical data. Because whether you have a medical data or medical image, whether you want to compress it, decompress it, filter it, and anything, they're all intrinsically done at the hardware level by the underneath hardware processor that is responsible for that. And these are not usually done by the general purpose processors that you see that are part of desktop or CPU machines. They are dedicated hardware processors which are known as intellectual property cores. But these internet technologies, since it plays a pivotal role in transmitting medical data, for example, for teleradiology and telepathology, the problem here is that the size of these medical data generated from MRI or CT scan is extremely large. Okay, so therefore large storage capacity is required to store. Moreover, when the large size of medical images is transmitted over the internet for remote diagnosis, it also needs large bandwidth. That's another problem, right? So in short, excessively large size medical data cannot be efficiently stored and transmitted. So any of the hospitals that you see around, they do not have a very large size of medical images of the patients. They somehow find a way to store it in a compressed format. I also would like to give you a motivation of why I'm saying this. For example, if you have a CT scan image of an abdomen, okay, so this is extracted from one of the doctors at Fortis Hospital that have collaborated upon. You see that the CT abdomen image comprises of usually 200 to 400 images, okay, where each slice of these images have 512 cross 512 pixels. I'm just taking not a very high resolution, but still enough. And each of these pixels could be a 16-bit information, okay? So therefore, the whole data set of the CT abdomen image would be somewhat around 150 MB of the storage capacity. Now, since it's huge, just imagine just for one patient, it is 150 MB. So this demands compression of medical images for low capacity storage and low bandwidth transmission. Okay, but the most important thing to understand is there is a trade-off involved here, that while you do the compression, the quality of the region of interest should not get distorted. So therefore, lossy compression under acceptable limit of compression ratio can be performed for medical images. And however, this acceptable limit of compression ratio varies for different imaging modalities and different body organs. Next slide, please. So why secure? Why secure these image processing codec processors for medical imaging? In case of both hybrid compression and lossy compression, hybrid compression means when you have a combination of lossy and lossless compression together. So in case of both hybrid compression and lossy compression, in an acceptable limit, JPEG compression can be applied. Okay, JPEG compression is useful, and that has already been adopted as a standard by the industry and by IEEE. However, stringent performance and power constraints entail using of dedicated processor for compression and decompression. That's what I just said, that you cannot use a desktop CPU for performing image compression and decompression. There has to be dedicated co-processors that are augmented as part of the microprocessor or motherboard, which is responsible for performing these operations. So the integrity and correctness of the medical data is important in these compressed medical images. So why it is important? Because we want to avoid wrong diagnosis of diseases, right? If the integrity and correctness of the medical data that the hardware generates becomes incorrect, it could lead to wrong diagnosis, or it could lead to a different sort of a problem for the patient during treatment. So therefore, these compressed images treated or generated from fake or unauthenticated JPEG codec hardware, which could be a counterfeited cloned one or could have a malicious logic such as hardware Trojan inside it, they cannot be fully trusted. So we will have to find a way to ensure before it gets integrated into the medical system, that the hardware that you're using is a trusted one. That means the hardware that you're using must be an authentic hardware, or it should not have any sort of hidden backdoor Trojan inside it. So the genuine diagnostically important pixel post compression of the medical images may be altered or corrupted, as I said, and that cannot be tolerated. We should have zero tolerance for this, and it could be a huge problem or catastrophic consequence, as it could mislead a healthcare professional during diagnosis process, leading to false diagnosis of diseases and wrong treatment of patients. Okay, now in order to keep the correctness of the generated compressed data, the underlying JPEG compression hardware therefore needs to be secured and trusted. So how do we do that? Next slide, please. So one of the ways to do that is to employ first line of defense using obfuscation and using second line of defense using steganography. So using first line of defense through obfuscation would mean that we are trying to impede the insertion of backdoor Trojan into the design using the process of reverse engineering. So it is a method to stop reverse engineering process of the JPEG codec processor, basically. So we can use obfuscation as first line of defense, and in the second line of defense we can use hardware steganography, which, if you recall, as I said, is a process to implant secret digital information into the design using secret constraints. So using the process of detecting of stego information in the design, we can easily find out if the design is a cloned, counterfeited, or an authentic one. So in totality, we are handling both the branches of cyber threat, which is the reverse engineering based Trojan insertion and also the piracy angle. So using double line of defense, we can actually secure against both the problems. Next slide, please. So hardware threats, Trojan insertion is one, counterfeiting and cloning. We have three different types of threats that we are talking about. The thwarting mechanism, which is the preventive control mechanism, is structural obfuscation, and that could be applied for, or to prevent against Trojan insertion and also to thwart counterfeiting process and cloning process. So how is structural obfuscation done? We convert the design of circuit into a non-interpretable form, okay? And that would make it difficult to understand and analyze the hardware. So therefore, the hindering of reverse engineering and malicious Trojan is possible. So tampering is prevented using this method. Or at least we could say tampering is made more challenging to an attacker using this method. The second is known as detective control, because here we are not trying to do any active mode of protection by doing preventive control. We are doing passive mode of protection by detecting if the piece of hardware that is used is authentic or pirated. Next slide, please. So these are some of the CT scan images that have been generated by the JPEG codec processor that we have designed in our lab. And these JPEG compression hardware that we have designed was a secured one. That means it had the deployment of double line of defense using structural obfuscation and hardware steganography. And as you could see that the reconstructed image that was having the acceptable level of quality that was desired for the specific body organ and imaging modality. Next slide. Okay, now let me move into another aspect of cyber threat. Okay, this is known as something known as functional locking or functional obfuscation. So how a piece of hardware in a consumer electronic device can be compromised. So consumer electronics could be your phone. Okay, that could be your iPhone, that could be your smartphone, that could be your smartwatch, that could be a smart home, that could be an IoT framework, that could be a wearable electronics. There are so many, I can just keep going. So consumer electronics is ubiquitous, it is omnipresent, it is there everywhere basically. So in this process, you see that the reverse engineering can be launched either from the stage where the netlist is created, or it could be launched from where the masking is done, or it could be launched from the packaging stage, or it could be launched from the stage where market ready functional IC is available. Once the reverse engineering is done, it gets hold of the locked netlist. So what is netlist? Netlist is nothing but just a file that contains information of the interconnectivity of all the gates of the design. Okay, gates as in like the Boolean logic gates that we are talking about. So once it gets hold of the locked netlist, then it can perform certain attacks on the locked netlist, such as key sensitization based attacks, such as SAT attack, such as removal attack, in order to get a deciphered netlist. Once it gets hold of the deciphered netlist, it can easily insert Trojan in that, and it can also perform cloning and counterfeiting of that. So how to prevent it? So let's see how we can apply functional encryption or functional locking to do that. Next slide, please. So as I said, in the key sensitization process, once you have the locked netlist with you, you can apply key sensitization attack on that to get hold of the deciphered netlist. Now this sensitization attack can be of one of the following ways. Either you can use the or exploit the isolated key gate problem in a structure, or you can have a run of key gates. Now in an isolated key gate, there is no path between K1, K2 as you could see, and thus they are called as isolated key gates. So the attacker can sensitize the value of K1 into the output by applying a certain input vector pattern, which is 100, and the rest could all be don't care. Similarly, if you have a run of key gate, it also becomes easier for an attacker to launch key sensitization based attack. And thirdly, the mutable key gates could also be a problem. If two or more key gates converge but have no common path between them, then also one of the keys could be sensitized to the output. So these are one of the three possible ways of performing key sensitization based attack to convert a locked netlist into its respective deciphered netlist form. Next slide, please. Now, let us talk of what are the ways to actually secure it. Okay, so one of the ways to secure it would be to use something called IP core locking blocks. So these IP core locking blocks are those blocks which are added at the output of every functional unit in the RTL structure, and they will only allow a respective bit to transfer to the output if the attacker is able to apply the correct key combination from K1 to K8. So for every output bit that needs to be deciphered, an attacker has to apply the right combination of 8 bits for every bit. Okay, so that's how these locking blocks look like. So these are just some examples of the locking blocks. They do not have a fixed template. The reason why they do not have a fixed template is just to keep it safeguarded from removal attack, because removal attack is another type of cyber attack where what is possible is the entire locking block could be removed from the design. And if it is removed from the design, then that encryption done using the key will completely become null and void. So in order to evade the removal attack, what is done is that different forms of IP core locking blocks are used. And these IP core locking blocks are thus reconfigurable by nature, and reconfigurability of these locking blocks could be obtained using value, and the encrypted value will only be known if the attacker knows the secret 128B input of the AES. So therefore, these IP core blocks don't have a fixed template. They rather are deliberately made reconfigurable so that they cannot be traced by the attacker in order to remove from the netlist file. Next slide, please. So this is one of the designs of a 4-bit FIR finite impulse response filter that we have designed in the lab. And the red colored gates are the ones which are reflecting the ILBs, intellectual property locking blocks. The remaining ones are the ones which are part of the gate design by default. So this has been the netlist representation of the 4-bit FIR filter. And you can see that the entire structure is a combination of basic gates. So it does not become easy for an attacker to identify what is part of ILB and what is part of the regular structure. Next slide, please. Okay, so I'm pretty much done with what I was talking, and the basic essence of the today's talk was to highlight the fact that cybersecurity is not now just a domain of cyber, software-based cybersecurity or data security or network security. The time has come when hardware cybersecurity needs to be given enough importance. There are several, world-class research institutes in